So remember last time in level 3 in the knowledge base, we actually talked about kinematic equations. We derived them from our axiom equations. And so if you remember, I'll write those axiom equations and then I'll write the kinematic equations that we derived with sines and cosines. So remember that the first one was our average velocity in the x direction, and we defined that as our displacement over time. We call this equation number 1. And that's not a minus sign, just so you know that this is equation number 1. Then we had another average, if you guys remember, and it was the initial velocity in the x direction plus the final velocity in the x direction over 2. All right. So we had two velocities there, and both of them were averages. And then the last equation was the acceleration, and we were concerned with constant acceleration. And this was coming out to be the final velocity minus the initial velocity divided by time. This was equation number 3. So we took these equations and we developed some new ones, and we called them our kinematic equations. And they look like this. It was the initial velocity for the x times cosine of the angle times time plus 1/2 times acceleration in the x direction times t squared. Let's just call this equation number 4. And then we have yf minus y initial equals to the initial velocity times sine of the angle in times t plus 1/2 a sub y, or acceleration in the y direction, times t squared. Let's just call this equation number 5. These are the two equations that we're going to use momentarily. And I'm discussing this theory again, or I'm reiterating it again without the derivation. You can always go back and look at the derivation in the other videos. But I want to connect this to the experimental activity that's coming up shortly, and that is the calculation of the initial velocity. And so let's just have a gander. Let's just look at this for a quick second. I'm going to have a mini launcher. And this mini launcher is going to fire a ball straight out. And we want to calculate this initial velocity in the x direction. Because it's being fired straight out, it's just the initial velocity, period. When I say it's being, if it had some angle to it other than 0, then we would have part of our initial velocity in the y direction. So know that there's a spring back here that is compressed, and we release that spring with a trigger. Okay, has a little rope on it, and when we release it, it pushes the ball out. Remember Newton's first law: an object that is at rest tends to remain at rest, or an object in a straight line, an object in motion in a straight line tends to remain in motion in that straight line unless acted upon by an external force. And the spring is applying or supplying that external force in this particular case when this object is at rest. So the ball is going to land on a table. So it's going to have a look similar to this, and the velocity in the x direction will remain the same all the way throughout, will not change. Now the velocity in the y direction will change. Notice that it starts off with 0 velocity in the y direction, because of how we're firing it. And that's meters per second. And then it actually obtains some velocity in the y direction, thus it goes down. You guys see that? So just say v final y. Okay. We will have an initial position in the x. We will have an initial position in the y. We will have a final position in the x and a final position in the y right here. So those are things that we can look at. It's also going to have a time of flight. So it's going to have an initial time and it's going to have a final time. And we know that the time final minus the time initial is just going to end up being t. So this is pretty much how our experiment is going to look. We're going to take those two equations above, 4 and 5, and calculate the initial velocity.